My name is Li Zhizhao, a PhD student from Beihang University. My supervisor is Lili Wang. The title of our presentation is Gaussian Hand, Real-Time 3D Gaussian Rendering for Hand Avatar Animation. The authors are Li Zhizhao, Xuequan Lu, Runze Fan, Zhao Jiyan, and Lili Wang. In this paper, we propose a real-time 3D Gaussian rendering method for hand avatar animation. With an off-the-shelf hand pose estimation model, given an RGB image of the user's input carol driving pose out of the training set, our Gaussian hand can animate the trained hand avatar with the input pose, while keeping the hand avatar's original realistic appearance. In the training phase, our method takes a sequence of sparse field images of a user's moving hand and its corresponding roughly estimated manual parameters as inputs to train the Gaussian hand model. In the inference phase, given manual parameters, our Gaussian hand model can generate realistic and animated hand avatar with free viewpoints and free poses. Hu et al. Presents Gaussian avatar to create animatable human avatars represented by 3D Gaussians and achieves promising results. However, directly applying it to hand modeling faces distinct challenges. First, hand geometry shows both pose-dependent variations and pose-independent consistency. The pose-dependent geometric features like wrinkle depressions dynamically deform with various poses. On the other hand, the hand geometry exhibits a pose-independent consistency, such as the position of wrinkles and vessels. Though Gaussian Avatar achieves pose-dependent geometric modeling, it does not account for pose-independent consistency, which is crucial for achieving realistic and stable hand rendering. Secondly, Gaussian Avatar lacks accuracy for pose deformation. Gaussian Avatar use linear blend scaling for deformation. The initial scaling weights assume that the unposed canonical Gaussians lie on the SMPL surface. However, during optimization, the unposed Gaussian offset from the SMPL surface, resulting in a misalignment between Gaussians and its scaling weights. Our method has three main steps. The first step is to estimate animatable hand Gaussians properties. We initialize unposed canonical Gaussians on the model surface. Through the standard linear blend scaling, we can achieve the initial post Gaussians. Our network estimates the Gaussian color, scale properties, as well as other necessary properties of our proposed modules. The second step is to use hand Gaussian blend shapes to model the non-smooth hand surface. The geometry of canonical Gaussians are optimized by the position offsets of our hand Gaussian blend shapes, which are composed of the learned Gaussian shape basis and the blend coefficients to achieve blend-shaped Gaussians. The third step is to use linear blend scaling with neural residual skeleton to deform the blend-shaped Gaussians and attain the final post-blend-shaped Gaussians for splitting rendering. The neural residual skeleton and the learned residual scaling weights together act as a residual term to rectify the linear blend scaling. We compare our Gaussian hand with recent state-of-the-art animatable hand avatar methods with publicly available code, including hand avatar and leaf hand. Our Gaussian hand demonstrates the best rendering quality on all three sequences with only 20 training views or 5 training views, while the baseline methods are trained with 139 views. Here we show the quantitative experiments. Hand avatar's nails lack realistic colors and shapes, and leaf hand nails appear blurry. Our Gaussian hand can render high-fidelity fingernails. For blood vessels, hand avatar only reconstructed the obvious veins in the lower right, ignoring the more stable ones on the upper left. Leaf hand tends to blur the thread-like vessel shapes. In contrast, Gaussian hand can render the blood vessels on the back of the hand. For shape consistency, hand avatar tend to reconstruct the fingers to be overly rounded, and leaf hand fingers tend to have unnatural bumps at the contours. Our Gaussian hand can maintain the consistency of finger shapes across different poses. For wrinkles, leaf hands results are blurry, and our Gaussian hand can render realistic wrinkles on the palm. We show more comparison results of our method with leaf hand in varying poses and views. The animation rendering of our method is more consistent with ground truth. The reconstructed nails have wide edge, consistent with the ground truth, while leaf hand nails color is flat. We also compare our method with harp on the hand appearance dataset. Our Gaussian hand reconstructs hand appearance with greater fidelity than harp. Thanks for everyone's listening.